So lecture 3F involves a concept called selective precipitation. And the math of it is a little bit weird, but once you get the hang of it, hopefully you'll find it actually pretty cool. So let's take a look at separation of ions. Many ions can be separated from each other by a precipitation reaction because of differences in reactivity or because of their charges. So let's say, for example, I had a solution of sodium chloride. So I would have sodium ions and chloride ions. And I wanted to separate the sodium ions from the chloride ions and out of the solution. So I wanted them in different solutions. I didn't want them together. Well, that's actually really easy to do with silver. We know that silver will precipitate chloride ions, and so that effectively removes them from the solution, leaving just the sodium ions and whatever counter ion the silver came in with, maybe like a nitrate or something. But it removes that chloride from that solution. However, sometimes you may have two ions that are too similar chemically in order to find something that'll precipitate one, but not the other. Let's say that we had a mixture of salts, and one was a bromide salt and one was a chloride salt, and they're both soluble in water. I want to try to separate bromide from chloride. This can really be difficult because chemically, these two ions are virtually identical. They react with pretty much the exact same things. They're in the same group in the periodic table, which means they share a very common chemistry. As it turns out, however, we can still use the silver ion to separate silver bromide from silver chloride. Both of these ions, bromide and chloride, will form a precipitate with silver. However, we can still use our silver, and we'll take a look at how. So it uses this idea of selective precipitation. Let's consider a solution that's actually a little more complex with chloride, bromide, and iodide. Now we've got three halide ions in there, all sharing very similar chemistry. All three of these ions will form a precipitate with silver. However, they form a precipitate at different concentrations because they have different KSPs. So the KSP for silver chloride is 1.8 times 10 to the minus 10. Our KSP for silver bromide is 5 times 10 to the minus 13, and our KSP for silver iodide is 8.3 times 10 to the minus 17. So fairly significant differences between those KSPs. Now, since the KSP of silver iodide is least soluble, this means that as silver is added, the I minus, the iodide ion, will precipitate out first as silver iodide. Then at some point, as that silver ion concentration increases, the bromide ion will then start to precipitate out, and then the chloride ion eventually as silver chloride. So that's a very qualitative way of looking at it, but let's look at something a little bit more quantitative. So let's say that we have a solution that has both the chloride ion and the bromide ion in it. They're both at 0.02 molar in this solution. We're going to add a source of silver nitrate, very slowly into that solution. We want to know what concentration of silver is needed to start precipitating silver bromide, and then at what concentration of silver will begin to precipitate silver chloride. Well, we can use our KSP values to do that. Looking at the KSP values from the previous slide, we know that silver bromide will precipitate first. It has a KSP of 5 times 10 to the minus 13. It's just going to be AgBr goes to Ag plus Br minus. And so our KSP expression becomes KSP is equal to the silver ion concentration times the bromide ion concentration of 5 times 10 minus 13. I know my bromide ion concentration is 0.020 molar. And so I just need to solve for my silver ion concentration. So my silver ion concentration, where precipitation begins for my silver bromide, is 2.5 times 10 to the minus 11. So I would need to use a very dilute silver solution and also have small drops into a fairly large beaker so that the concentration of silver going into that beaker would end up being 2.5 times 10 to the minus 11. So that's where precipitation starts. And at that point, I start to precipitate out silver bromide, and my chloride will still remain in solution because its Q for the silver chloride will not have met the KSP for silver chloride. So as I start to slowly add silver ions in these rough concentrations, I'm only precipitating silver bromide out. Now what about the Cl? What about the chloride minus? Well, I know that I'm going to have the same basic KSP expression, silver plus times chloride minus. The KSP is different. It's 1.8 times 10 to the minus 11. So I plug in my 0.02 value for the chloride ion concentration to calculate the silver ion concentration I need to reach in order to start precipitating out silver chloride. And that's 9 times 10 to the minus 9. Now, if my silver ion concentration is in the 10 to the minus 11 when the silver bromide starts precipitating, how do I ever get to 9 times 10 to the minus 9? Well, we have to start thinking about what's going on. So I start precipitating silver bromide out. And the silver, and my silver is at something times 10 to the minus 11. The silver chloride precipitation won't start until my silver concentration is almost 100 times greater than that, at 10 to the minus 9. Now, as I precipitate silver bromide out of that solution, the bromide concentration in that solution begins to decrease. And so as the bromide ion begins to decrease because it's being precipitated out, the concentration of silver that I need to add in needs to increase in order to match the KSP value and saturate the solution and precipitate silver bromide. So eventually, my silver concentration goes up and up and up from the original 10 to the minus 11. Once it reaches that 9 times 10 to the minus 9, then at that point, I'm right at the threshold of being able to precipitate silver chloride. And at that point, I have separated out the ions as much as we possibly can. Okay. So what is that point? What's the concentration of bromide once I reach that concentration of silver at 9 times 10 to the minus 9? So before I separate the silver chloride, what's the concentration of the bromide? So for that, I actually need to use the concentration of silver at the chloride part. So where silver chloride begins to precipitate, silver ion concentration is 9 times 10 to the minus 9. I go back to my KSP for silver bromide. I know that right when the silver chloride wants to precipitate out, my silver ion concentration is 9 times 10 to the minus 9. I want to know my bromide ion at that point. And so I use the KSP for my silver bromide. And I see that my bromide ion concentration is 5.56 times 10 to the minus 5. So how well did we separate out the chloride from the bromide? You can never do it perfectly. You're never going to get all of it out before you get something else out when you have things that are that chemically similar. However, considering that we started with 0.02 molar bromide, and we finished with 5.56 times 10 to the minus 5, we've actually removed 99% or 99.7% of the bromide ion away from the chloride ion. So that's actually pretty good. So selective precipitation is a little bit complex to visualize. The math can be confusing. You just have to keep track of what you're calculating and why you're calculating it.